There is grandeur in this view of life.
Welcome to Evolution Talk with Rick Coast, an introduction to the oldest story ever told.
My scientific studies have afforded me great gratification, and I'm convinced that it will not be long before the whole world acknowledges the results of my work.
We would all like to think that the work we do will someday be acknowledged. Sooner rather than later would be better, and while we are still alive would be even more preferable. And this is what Gregor Mendel hoped when he said those words, that his efforts would pay off. He wasn't necessarily looking for personal gain. He was a monk after all. To be more specific, he was an Augustinian friar, a follower of St. Augustine. He was not concerned with money, except of course when it affected the order, which we will see later. But at this point, when he remained convinced that his scientific studies would be recognized, he had, essentially, two masters, the order being one and science the other. He was a man walking a tightrope between two worlds. Mendel wasn't going to get his wish, at least not in the way that he'd hoped and prayed. Gregor Mendel was born as Johann Mendel in Austria in 1822, and his family owned a farm that had been run by a line of Mendels for over a century, and needless to say, his family did not have a lot of money. When it came time to seriously consider an education, Mendel found that he was extremely interested in how things worked. He was very adept at being a beekeeper on the farm, and the bees fascinated him. Gardening fascinated him. He would spend hours trying to figure out how everything fit together. The only thing holding him back was a proper education. He knew that, with a little knowledge, he could figure something out. What that something was, he wasn't quite sure, but he knew he was meant to do more than to tend the family garden. And so he decided to become an Augustinian friar, and he joined the St. Thomas Monastery. And why? Because they would pay for his education. Not exactly the most noble reason, but once there, nobody could question his faith or his dedication to the order. As with anything else, Mendel threw his heart, mind, and body into it. When he wasn't learning about the order, he was holed up in his room with a book. That's not to say that the order took him in for noble reasons either. It's not like they took one look at the son of a peasant farmer and immediately agreed to adopt him as one of their own. The abbot of the monastery was well aware of Mendel's choice of study and the fact that Mendel approached gardening in a more scientific way than most people did. He being the abbot, felt that Mendel could help the order just as much as they could help him. If his efforts proved fruitful, and by fruitful that meant better fruits and grapes, then maybe the monastery could refill its coffers. They didn't have a lot of money either. They still needed money. There were bills to pay. Except taxes, of course. Under German law, the monastery was exempt from paying taxes. Now, Mendel's interests grew. Along with the mysteries of nature on the ground, he was also transfixed by the mysteries of nature above his head. He tracked clouds and weather patterns, eventually co-founding the Austrian Meteorological Society in 1865. Now, while he was doing all of this, there was another aspect of nature that continued to capture his attention: heredity. As mysterious as predicting weather patterns were, predicting and understanding how heredity worked had its own set of hurdles. Hurdles that remained invisible and thwarted pretty much everyone who attempted to study them. Even Charles Darwin had a hard time explaining it. While Mendel was tracking storms and forming his own thoughts on the subject of heredity, Darwin was proposing that heredity involved little things called gemmules. Now, these gemmules, Darwin thought, passed from parent to child and contained information about how to form different body parts. There was a gemmule for hands and one for feet. There were also things to consider, such as eye color, shape of one's nose, and also the color of one's skin. A child might receive a gemmule from each parent that dictated eye color. One might express itself while the other one floated around in their bloodstream to eventually be passed on to their children. And that's why certain traits skipped a generation, or so they thought, or even generations, before expressing itself. This theory was known as pangenesis, and Darwin continued to work on it throughout his life. You have to remember, he knew nothing about genes or DNA. Nobody did. And that was all decades away, and not to be studied until well after he himself had passed on. Mendel, too. Now, while Darwin was busy scribbling notes on the subject in England, Mendel was having a little bit more luck in Austria. There was another theory that was popular among biologists at the time. This one was called blending. It too assumed that traits were inherited from both parents. But unlike Darwin's gemmules, these traits didn't dictate precisely what would happen. Now, say for instance your father had large feet and your mother had small feet. According to Darwin's theory, there was a gemmule for each specific feature of a foot. Each toe may have its own gemmule. So your big toe might be the result of your father's gemmule, your pinky toe from your mother's. What blending suggested was that all of your features were a blend of both parents. Your big toe wasn't specifically your mother's or your father's, it was a blending of both. This blend was unique to you, and you would pass it on to your child who would blend traits from you with traits from their other parent. It was what made each of us unique. Mendel wasn't buying this. It didn't fit with what he was seeing. Mendel began to spend more and more time studying heredity. He started off with mice, but the abbot of St. Thomas wasn't particularly keen on one of his friars obsessing over what he thought of as animal sex. And on top of that, he felt that mice were dirty little creatures. So to appease the abbot, Mendel turned to a safer avenue: peas. Peas were much more acceptable, of course, than mice. Plus, they had the added benefit of not requiring as much room or attention as mice. The monastery's nursery was the perfect spot for Mendel to conduct his research. And peas had something else going for them. They had easily observable traits that expressed themselves in one of two ways. For example, the pea plants in the nursery were either tall or short, they either had purple or white flowers, and produced seeds that were either yellow or green or were round or wrinkled. It wasn't a blend of traits. It wasn't like the seeds were a color somewhere in between yellow and green. They were either yellow or green. What Mendel didn't know, but which we know today, and which made peas the perfect subject for study, was that this difference was dependent upon one gene. One gene dictated the color, the dominant gene. But, of course, Mendel didn't know this. Nobody did. Genes weren't a thing. But he isn't called the father of genetics today for no reason. Mendel's star was about to rise, even though, like a shooting star, you would miss it unless you happened to look up at the right moment. Unfortunately, nobody did. Another thing that made peas perfect for study was the fact that the plant itself has both male and female sex organs. This means that they don't need other plants to pollinate. They can, well, pollinate themselves. Now, obvious jokes aside, Mendel could make sure that he was producing purebreds by self-pollinating the plants first before cross-pollinating them. Now, it worked like this. By focusing on one trait at a time, he could track the appearance of that trait over generations. Now, let's pick the shape of seeds. They were either round or wrinkled, as I mentioned. Now, to make sure that he had purebreds to start with, he would self-pollinate the round pea plants with themselves and the wrinkled pea plants with themselves. Round pea plants, when self-bred, produce only round peas. The same went for the wrinkled peas. Now, after a few generations of this, he consistently saw either round peas or wrinkled peas. These were his base, his control. He then took a deep breath and cross-pollinated the round with the wrinkled. And what did he see? Well, the first generation of cross-pollinated plants had round peas, and this told him early on that round must be the dominant trait. So he took those plants with the round peas that were the result of cross-pollination, and he self-pollinated them again. And he saw his first wrinkled peas appear in the second generation. Now, what this told Mendel was that the trait was there and didn't express itself until the next generation. And the more he did this, the more he began to see a pattern. So he started to count the results, one by one. All in all, he counted 5,474 round peas and 1,850 wrinkled peas. This came to a ratio of 2.96 to 1. Now, every time he did this, he found after a number of generations a similar ratio. Sometimes it might be 2.96 or maybe 2.98, but always close to 3 to 1. And it makes sense when you think about it. Cut the music. Remember, this is one gene here. The P is either round or wrinkled, and round is the dominant trait. Now, we'll use a big R for the round gene and a little w for the wrinkled gene. The results can be one of four possibilities. Either two round genes, which are two big R's resulting in a round P, and then you might have a big R and a little w, R being the dominant one, so you'll see a round P. And then there's the opposite where you have a little w and a big R. Again, you'll get a round P because the big R trumps the little w. So the first three combinations always result in a round P. The last combination is two little w's, which result in a wrinkled P. So out of four combinations, the wrinkled P will appear once. Thus we have the 3 to 1 ratio. And this became the golden ratio. 3 to 1 is the gold standard of genetics, even if the number itself is slightly rounded up, which, to be honest, has caused quite a bit of controversy and debate among geneticists over the years. Now, did Mendel already intuit that 3 to 1 ratio and work towards proving it? Or did he realize where it was heading and steer his results towards it like a captain on a genetic ship? Either way, he was right, and the experiments, testable and reproducible, proved it. So Mendel did what any good scientist would do. He pulled it all together, and he produced a paper which he read to a group of his peers in 1865. The paper was all about his peas and his heredity experiments. Now there too was the golden ratio and the math that led to it. Math. Nobody likes math. So they listened and forgot about it. Mendel then published his paper as experiments on plant hybrids. He produced 40 copies and he waited. Nobody stood up to validate his results or his conviction that
it will not be long before the whole world acknowledges the results of my work.
Mendel faded into obscurity. It wasn't total obscurity, however. In the silence that followed, he slowly removed himself from experimenting on pea plants. Round or wrinkled, yellow or green, it didn't matter anymore. And plus, he was elected abbot of the St. Thomas Monastery. This kept him busy, but he was too busy to worry about his peas. And in 1874, about 6 years into his tenure as abbot, the Austrian government revoked the monastery's tax-exempt status. All monasteries, in fact. They, like every other institution, had to pay to the government 10% of the monastery's value. Now, what did the acting abbot Mendel do? He stood his ground, and he refused to pay it all. And when the authorities showed up to seize some of the monastery's assets, Mendel met them at the door, locked the door behind him, and dared them to remove the key from his pocket. Which they didn't. Mendel had won the battle, but he lost another. In 1884, Mendel died of organ failure. That probably attributed to his unhealthy lifestyle, surprisingly. He loved his cigars, and not a moment went by where you wouldn't see one dangling from his mouth. He was 61 years old. Now, had he lived a couple of decades more, he would have seen an amazing thing happen. While he may have given up on his work on heredity, the rest of the world hadn't. Scientists and enthusiasts had continued to make headway into uncovering the mechanics behind it. They were gradually rediscovering what he had already found. At the turn of the century, 3 biologists, independent of one another, stumbled across Mendel's work. Remember those 40 copies that Mendel had made of his pea paper in 1866? Many of his papers had been burned by the monastery after his death, but copies still floated around. These copies fell into the hands of 3 biologists almost simultaneously, as if Mendel himself was working behind the scenes to ensure that they did.
It will not be long before the whole world acknowledges the results of my work.
These 3 were Dutch botanist Hugo de Vries, German botanist Karl Correns, and the only American of the little group, William Jasper Spillman. all three were on to the golden ratio. De Vries may have been the closest. While working to unlock the mysteries of the ratio, De Vries came to the conclusion that traits were inherited by little particles passed from both parents to the child, and that similar traits always had one, which was dominant. Now, he came across Mendel's paper at the perfect time, and when he published his own paper on the subject, he never mentioned that Mendel had gotten there before he did. Luckily for Mendel, Karl Correns, the German botanist, had also rediscovered Mendel's paper and recognized Mendel's barely concealed contribution to De Vries' work. Now, Correns called De Vries out on it, and De Vries, perhaps begrudgingly, acknowledged Mendel as having been way ahead of them. As Correns explains it,
I thought that I had found something new, but then I convinced myself that the abbot Gregor Mendel in Brunhead during the 60s not only obtained the same result for extensive experiments with peas, which lasted for many years, as did De Vries and I, but had also given exactly the same explanation, as far as that was possible in 1866.
It sounds weird hearing him refer to the 60s and it not being the 1960s, doesn't it? So today, Mendel is recognized as being the father of modern genetics. He and his peas illuminated the way for all that followed. It's almost as if he had planted a seed which only needed time to germinate.
The gardener plants seedlings in prepared soil. The soil must exert a physical and chemical influence so that the seed of the plant can grow.
That was from a sermon that Mendel delivered himself on Easter Sunday, 1847. He was quite a gardener. Evolution Talk is written and produced by myself, Rick Coast, and the music on this episode was composed and performed by Poddington Bear. And support for Evolution Talk comes from you, simply by listening. You can also help the show and its continued existence by visiting evolutiontalk.com/support. And most of all, thank you for listening. And until next time, please take care of yourself.
Evolution Talk is a Rick Coast production.